everyone, my name is Rosito de Orquesta and welcome to Pantasmalaya. So as a continuation of the previous uploads of the previous topics about platform technology, we will talk about um, process management. In the previous discussion, we talked about the major components of the operating system. And one of the major component of the operating system is the process management. So today we are going to talk about what is process management, what are the contents, what are the parts, the important parts of the process management. So a process management, as per definition, is a program um, in your inside your central processing unit in your operating system. So these two process management are interconnected, interrelated to each other. So a program does nothing unless its instructions are executed by a CPU. A program is execution, and execution is called a process. So all those things that happen inside your central processing unit or in your operating system, both are called a process. So in order to accomplish its task, process needs the computer resources. There may be exist more than one process in the system, which may require the same resource at the same time. Therefore, the operating system has to manage all the processes and the resources in a convenient and efficient way. So since most of the computers, especially the current generation of computers that offers multitasking, it process different instructions simultaneously. So those processes should be managed in some way. So attributes of a process are used by the operating system to create the process control block or the PCB for each of them. This is also called context of the process. Attributes which are stored in a PCB are described on the following slide. The first one is the process ID. So a process ID has just an identification that lets the process manager to identify the current process or the next and so on. So when a process is created, a unique ID is assigned to the process, which is used for unique identification of the process and the system. When I say unique, there is no two or three process that has similar or the same ID, process ID. It is a unique header, a unique pointer, or a unique identification of a process that is created in your operating system. So you're going to start to print, you're going to start a Word file, you want to save a current open Photoshop image. Those different processes should or will be assigned a unique process ID. The second one is the program counter. A program counter stores the address of the last instruction of the process on which the process was suspended, and the CPU uses this address when the execution of this process is resumed. So when, say for example, a single process or two to three processes are halted, it is being paused. Say for example, in this table below, so we had at least four processes. Now for the process with PID 000, the first process, it is in a waiting state because it waits for the user input, and in this time, since it is waiting for a user input, it will be suspended, or it will be paused, it will be halted from continuing the process. So but that current operation will be stored in a program counter with a specific address. So for example, the common address is the CH or the CL addresses in your program counter. And the third one is the process state. So the process from its creation to the completion goes through various states, which are new, ready, running, and waiting. So this will be discussed in a more detailed on the next slides. So it is new if it is just created, and when it is created, it's always ready to be executed. And if does not require additional input, it will run. It will be processed in the central processing unit for possible additional input, or to terminate the action to present a result. Or it could be waiting if it waits additional resources from the user, or it will be halted due to the lack of memory to run the process. So the number 4 is priority. So in process management, there are these priorities. So every process has its own priority. The process with the highest priority among the processes gets the CPU first, and this is also stored on the process control block, or the PCB, to determine which are those processes that needs to be executed first, second, third, up to the last, or maybe at the same time. So as you can see in the table below, there is a priority, a sample priority list. Say for example, we had a too high and too low. So as for the PID 001, the current process which is currently running, since it is currently running and it is high, it is placed on the first row of the PCB, while the PID 003, it is also high, but it is a new process, so it is ready to be processed. But since the 001 is the one currently on the process, so the new process with PID 003 will be put into the second in the queues, while the PID 002, or the last process, will put into the last row of the PCB. It is because compared to the PID 000, or the first process which is waiting, maybe it is waiting for an input, an additional input from the user. So since it is already processed or run, but just paused or halted because of some additional input from the user, maybe, or from the other device, and it is put in a waiting state, so it should comes third from the PCB, while the PID 002 will be put into the last row of the PCB, since it is a low priority, and it is although it is ready, compared to the PID 00, which is already run but just halted because of an additional input, maybe from another user, from the current user, or from a certain device, a peripheral or input device. Okay. And then the fifth one is general purpose registers. So every process has its own set of registers which are used to hold the data which is generated during the execution of the process. See, we have this example with PID 00, 001, 002, and 003. Since these register, these processes are instructed into the operating system and to be run by the central processing unit, all these processes has their general purpose register. So it is now allocated in a register, or in a cache, or in a memory, in a computer memory. So these cache, these spaces are represented by BL, EX, EH, EL. So these are some examples of the general purpose registers in your central processing unit, in the CPU, in your cache. So these BL, EH, EX, or EL, those are specific location in your machine, in your cache, or in your central processing unit. So we called it these uh, four as general purpose registers. Then we have the list of open files. So during the execution, every process uses some files which needed to be present in the main memory. So OS also maintains a list of open files in the PCB. So say for example you're opening different kind of files while you are using the computer. So your operating system keeps track on that open files, and also creates a list of these open files in your program counter, or in the PCB, or the PC program counter block, a process control block. So all the open files will be also stored in your process control block or the PCB. The number 7 is the list of open devices. So OS also maintain the list of all open devices which are used during the execution of a process. So since the process of a computer is will not be most of the processes in a computer will not be complete without input and output. So and most of our inputs and outputs peripherals are devices, a list of devices. So your operating system will keep track on these devices that the processes will be using, like where should the process gets the input, where should the process display or manifest the result of the process inside your central processing unit, the output. So your operating system is also managing this list of open devices aside from the list of open files. So let's have a recap. A process management, it has a process ID, a unique identification for a process. It has a program counter, which will save the last instruction, or the last instruction or the next instruction that is ready to be performed. Then the process state of all those processes, the new, the ready, the running, and the waiting. And then the priority, which of these processes will be executed first, second, simultaneous, or the last to be executed. It also had the general purpose registers. So these are the specific cache or space that is allocated to each of the processes when it is created, and when it is processed or processing, and when it is producing a result. It will keep your operating system as well as the process management will keep a list of open files that is used as a resources in your process of the current process, and it will also keep a list of open devices which will be the source as input for the process, and the output as where the result of the process will be manifested or passed. So these are the complete process attributes. So we have the process ID again, a program counter, a process state, priority, a general purpose registers, list of open files, and list of open devices. Now I have here a sample diagram of the process of a process. This is how a process management works inside your operating system, your computer. So as you can see, we have here a new process. This new process passed to the ready state. It is now ready to be executed. Since it is ready, it will be scheduled for dispatch. It will be run, then completed and terminated. So when it is already complete, it will be terminated or end. But there are some tendencies that it will not just go to termination or the end point, but say for example it will be suspended. Now, some processes will be suspended but put on ready until it will be resumed. The scenario for this is, if say you have already exhausted your resources. So for example, your RAM is already packed with different open processes, and you still want to open a new process, but that process could not be scheduled for or dispatched for running the process because it requires a lot of resources. It requires at least, say for example, the current available space in your RAM is 500 MB, and that new process requires a 600 MB from your RAM. So there is not no enough space for that process to be dispatched. So that's why it will be suspended until a specific amount or an equivalent amount of free space in your RAM will be manageable to resume the process. Another thing is the priority time quantum. A priority time quantum will happen if um, your new process is not it has the low priority. So in the previous slides we talk about priorities, the high, the medium, and the low priority. So if that new process has the medium or has the low priority, so it will be put into ready. It will not run for completion. So, and also if that process is already on the run state, but during the run state it will request a new input. Say for example, if you are running a program which requires two operands like 1 plus 1, so in the first run it will ask you here to input the first number, but while it is running it will ask another input which is the next operand, and for that scenario it will be put into wait or block, and it will be suspended or resumed to wait and block. So how will it be suspended? It will be suspended if, say for example, with our example, the operation of two numbers, the sum of two numbers, where it requires you to input an additional number. If the user did not enter the second number, the second operand number, it will be that process will be put into suspension. It will be suspended since it is waiting for an input. Whenever the user supply the necessary input or the necessary requirement, it will resume that process and put into wait or block, and then back to ready, and then schedule for dispatch for the next run, which is to sum up the two number. So ready, schedule dispatch, enter the first number in the run, and it requires additional number, so it will wait for input. When the input is already given, or the second number, it will resume, and it will determine that the IO is completed, and then it will be scheduled to dispatch, run, present the output, termination. It could also be suspend and wait if you have already supplied the necessary or additional resources, but still it will not be resumed. It will be put to process completed IO, but still in suspension. And the reason is just like a while ago I give an example of the lack of space in your RAM. So you have already supplied the necessary or additional input or resources, but it could not proceed because there is not enough space in the RAM to run that process. So it will be suspended and ready, and when there is enough space in the RAM or in your memory, it will resume to ready state, then dispatch, run until completion or termination. So these are the basic or the actual process management inside your operating system in your computer. So this priority quantum here is a this priority time quantum, this suspension, this IO request are all intervening variable that could halt or pause or suspend the current process. Okay, so process attributes. The process from its creation to completion passes through various states. The minimum number of states is 5, at least 5. You can see here: new, ready, run, wait, and termination. So 1, 2, 3, 4, 5. So first three of the process attributes, we have new, ready, and running. So a program which is going to be picked up by the operating system into the main memory is called a new process. So creating a new process, it is ready whenever a process is created, that it directly enters in the ready state. Yes, that's true. In which it waits for the CPU to be assigned. The operating system picks the new processes from the secondary memory and put all of them in the main memory. Then the processes which are ready for the execution and reside in the main memory are called ready state processes. There can be many processes present in the ready state, but all these processes could not be executed simultaneously. Some of those maybe, but not all, because there are some that requires specific resources which are used by other currently running processes. Okay, so the running state, one of the processes from the ready state, will be chosen by the operating system depending upon the scheduling algorithm. So there are different scheduling algorithm, and hence there is a intervening variable regarding on the priority. So hence, if we have only one CPU in our system, the number of running processes for a particular time will always be 1. If we have n processors in the system, then we can have n processes running simultaneously. This means that if we could have a multi-core processor which could process different instructions at the same time simultaneously, then we could lessen the time, we could shorten the process, we can make the computer run faster than any other machine. Okay, so block or wait, this will happen when from the running state a process can make the transition to the block or wait state depending upon the scheduling algorithm or the intrinsic behavior of the process. So when a process waits for a certain resource to be assigned or for the input from the user, then the OS moves this process to the block or wait state, assigns the CPU to the other processes. And then for completion or termination, when a process finishes its execution, it comes in the termination state. All the context of the process control block will also be deleted. The process will be terminated by the operating system. It means it is already complete. It has already been processed and has given the necessary output or result from that process. So all its resources will be clear. All the used general purpose registers and other devices will be cleared, ready for the next process. So suspend ready is when a process in the ready state which is moved to secondary memory from the main memory due to lack of the resources. So mainly primary memory. So it's called in the suspension ready state. If the main memory is full and a higher priority process comes for the execution, then the OS have to make the room for the process in the main memory by throwing the lower priority process out into the secondary memory, and the suspend reader process remain in the secondary memory until the main memory gets available. So as I have said, so if these are we have two processes, this is low, this is high, and this will require this is already on the main memory, but then this new process is um, the priority is high, so it requires more attention. They will switch position. This one will be put into the secondary memory and this into the primary memory, so that this priority process will be executed first. The suspend wait, so instead of removing the process from the ready queue, it's better to remove the block process which is waiting for some resources in the main memory. Since it is already waiting for some resource to get available, hence it is better if it waits in the secondary memory and make room for the higher priority process. These processes complete their execution once the main memory gets available and their wait is finished. So suspend ready and suspend wait, these two works almost the same. So the difference is, while the suspend ready, the current process will be taken down to the secondary memory to give a space for the main memory for the process which has a higher priority. And the suspend wait, instead of removing the process from the ready queue, it's better to remove the block process which is waiting for some resources in the main memory instead. And then we have operations on the process. So we have 4: creation, scheduling, execution, deletion, or killing, or the termination of the process. If you say creation, once the process is created, it will be ready and come into the ready queue in the main memory. So instead of using the secondary memory, it will be moved into the main memory as ready process. And then scheduling, out of the many processes present in the ready queue, so all the processes when created will be submitted to the ready state and will be packed into the secondary or the main memory. But out of the many processes present in the ready queue, the operating system chooses one process and start executing it. Selecting the process which is to be executed next is known as scheduling. So it will be then depends on the scheduling algorithm as well as the priority. On the later topics, we'll talk about more on scheduling. Then the third one is execution. Once the process is scheduled for the execution, the processor starts executing it. Process may come to the block or wait state during the execution. Then in that case, the processor starts executing the other processes. So if this current created process is already scheduled and it will be executed, and when it comes to that this current process needs another input, so it requires an input or intervening or additional resources, it will be put into block or wait state. Then the next process will come to the scheduling for execution. So the first scheduled or executed process will be put on halt, will be paused to give way to the second process until this first process has given the resources, the additional resources it needs to complete the execution. And then during the deletion or killing, once the purpose of the process gets over, then the operating system will kill the process. The context of the process or the PCB will be deleted and the process gets terminated by the operating system. So when that certain process has finishes the commands, executing the commands, it will then be deleted from the process control block. Okay, all of the context will be removed from the process control block, and then all the resources that it used, the cache, the spaces in the memory, the registers will be released, will be empty, and all the files and other resources will be freed also after the deletion or killing of the executed process. about the process schedulers is an OS task that schedules processes of different states like ready, waiting, and running. So process scheduling allows operating system to allocate a time interval of CPU execution for each process. Another important reason for using a process scheduling system is that it keeps the CPU busy all the time. This allows you to get the minimum uh, response time for the program. So, say for example, there are different scheduler in the process. First one is the long-term scheduler. Long-term scheduler is also known as job scheduler. It chooses the processes from the pool or the secondary memory and keeps them in the ready queue maintained in the primary memory. Long-term scheduler mainly controls the degree of multi-programming, and the purpose of long-term scheduler is to choose a perfect mix of input-output bound and CPU bound processes among the jobs present in the pool. If the job scheduler chooses more IO bound processes, then all of the jobs may reside in the block state all the time and the CPU will remain idle most of the time. This will reduce the degree of multiprogramming, and therefore the job of a long-term scheduler is very critical and may affect the system for a very long time. Mostly, the best example for long-term scheduler are those jobs that when we say IO bound, it requires specific inputs. So it will always wait for an input, and it will also output bound. It requires a specific peripherals or device to be ready for the output. So it mostly the long-term scheduler waits a specific resource to facilitate the process. And when there are also the short-term scheduler. So if we say short-term scheduler, also known as the CPU scheduler, it selects one of the jobs from the ready queue and dispatches to the CPU for the execution. A scheduling algorithm is used to select which job is going to be dispatched for the execution. The job of the short-term scheduler can be very critical in the sense that it is if it selects job whose CPU burst time is very high, then all the jobs after that will have to wait in the ready queue for a very long time. So this problem is called starvation, which may arise if the short-term scheduler makes some mistakes while selecting the job. So short-term scheduler should select those if the long-term scheduler selects those processes or jobs that requires a longer time and a large time for central processing unit to execute, and mostly it requires an additional input or resource, or it will choose or bound to a specific output device which will halt the operation if that device is not present in the system. The short-term scheduler is mostly determined to select a ready queue or a ready state jobs which takes a slower time a lower time in processing. It will take minimal resources in your system. That is the concern of short-term scheduler. And when this short-term scheduler make a mistake, say for example the mistake is the scheduler think that this current job is will only consume 500 MB of your RAM, and then it will be executed in less than a less than 5 minutes, but then the actual process requires 1 hour, and then it consumes, instead of 500 MB in your cache, it will in your memory, it will consume at least 1 gig. So that is a lot of resources. So the short-term scheduler has missed the decision, then that's the time that it will create a starvation. A starvation, if you can still remember, it is when the current process, the current job performs a lengthy time, it requires a lot of time to be processed in the central processing unit. So the other jobs will wait until that current process will finish. And let's say if that current job will takes at least 1 to 2 hours, those other jobs that is waiting on the real estate will get starved. And then we have this medium-term scheduler. Takes care of the swap out processes. If the running state processes needs some IO time for the completion, then there is a need to change its state from running to waiting. So medium-term scheduler is used for this purpose. It removes the process from the running state to make room for the other processes. Such processes are then swapped out processes, and this procedure is called swapping. So the medium-term scheduler is responsible for the suspending and resuming the process. It reduces the degree of the multi-programming. The swapping is necessary to have a perfect mix of processes in the ready queue. So when a current job requires additional input, additional resources or specific output device, this job will be swapped to the next job. So the current job or the current process will be put into halt, will be paused, or while it waits for additional input or additional resources or specific output system or output device peripheral to give a way for other, so for example, short-term jobs to get executed while the current executed job is being put on hold or waiting state for additional resources. So that is the purpose of the medium-term scheduler. It will look into those jobs that needs additional input, so it will halt those process, then let another process go into the central processing unit to be processed, while this process waits for additional resources from the input, or wait until a specific device for output is plugged into the system. So this is the process queues. So the operating system manages various types of queues, and for each of the process states, the PCB or process control block related to the process is also stored in the queue of the same state. So if the process is moved from one state to another state, then its PCB is also unlinked from the corresponding queue and added to the other state queue in which the transition is made. So we have here, these are the queues. So job queue, new, it will put into ready, then it will have a schedule to run in the central processing unit, but there are times that it will add the algorithm, the scheduling algorithm will takes a fix here if it needs an IO intervention, so it will be put on waiting, then that event, and then pass to this event back to ready state CPU until it will be completed on terminated or killed from the process queues. So that's how the operating system manages the queues or the job processes inside the operating system or inside your computer system. So these are the following queues maintained by the operating system. First is the job queue. In starting, all the processes get stored in the job queue. It is maintained in the secondary memory. The long-term scheduler or the job scheduler picks some of the jobs and put them in the primary memory. So the long-term scheduler will select from this new jobs from the queue and put it into the main memory for primary memory for execution. Then the ready queue is maintained in primary memory. The short-term scheduler picks the job from the ready queue and dispatches to the CPU for the execution. So after this long-term scheduler puts some jobs into the primary memory, all these jobs that is now transferred in the primary memory will have a ready queue or a ready state, and then the short-term scheduler will pick from this job from the ready queue and dispatch to the central processing unit for the execution. And then the waiting queue will happen when the process needs some I/O operation in order to complete the execution. So it will wait additional resources, additional input or specific output device, and OS changes the state of the process from running to waiting. The context of PCB associated with the process gets stored on the waiting queue, which will be used by the processor when the process finishes the I/O. So while there is no supplied additional resources as input or a specific output system, this process will be put into a waiting queue. So the job queue are those jobs that waits for the long-term scheduler to be picked and transferred to primary memory and make it into a ready queue ready for processing or a dispatch into the central processing unit for execution. And during the execution of this process requires additional input from the user, additional resources. The medium the medium term scheduler will change the state of this process into a halt or a waiting or a suspension. It will get suspended and it will only resume after a certain requirement is met, had been met. Process management as the one of the major component of the operating system. Those are the things that needs to be understood, need to be studied, so that we can identify or we can understand and appreciate the works of your operating system in managing all the processes that is happening inside your computer machine. So if you have more concerns, if you have questions and clarifications, you can comment down below. Thank you so much.